I'm going to talk about competing mechanisms in training dynamics. So this is based on joint works with Mo Zhou, who was my PhD student and is now a postdoc, and he's also here. And another work is based on work with Kashav and Rico, who are two Duke undergrads, and my PhD student, Romin. Sorry for the slightly confusing title, and this is an idea that I'm still trying to formalize. So let me first try to explain what I mean. So first, let's think about some of the classical mechanisms in training dynamics. So the classical ways we know how to analyze training dynamics for neural networks. So a lot of the works fall into one of these two categories. One possible training dynamics is kernel-like. You can think about neural tangent kernel for neural networks. And in this regime, we understand the training dynamics fairly well. We know that neurons will not move very far from their initial position, and eventually the network behaves kind of like a kernel. There's another regime that, depending on the setup, sometimes in some examples are called mean field analysis, and some cases people just refer to them as feature learning, or sometimes people refer to them as reach regime. But in any case, in this different regime, neurons or whatever components that you have in your system are allowed to move by a lot. And the benefit of this phenomena is that it enables you to learn features, which is why it's considered the feature learning regime. And people have been working on analyzing the training dynamics for both regimes. And a lot of these analyses have some common properties. So first, usually when we are able to analyze the training dynamics for a certain problem, usually we have a unique desired solution. And I don't mean literally unique in the parameter sense, but I mean unique up to an equivalent class. So maybe, of course, you can permute the neurons, or maybe your desired solution depends on your random initialization, but we do have a clear desired solution for the problem. And in many cases, when we were able to analyze things or prove anything about training dynamics, there is a fairly clear trajectory from your initialization towards the desired solution. And finally, for many of these works, one of these two mechanisms is dominating. So either you are in the kernel-like regime, or you are in the feature learning regime, and you don't necessarily go between these different regimes. In this talk, what I'm going to try to say is that nowadays, when you look at some new problems, they often have these more interesting dynamics that are more complicated. And instead of trying to say I'm providing solutions to these new problems, this talk is more about asking more questions. So we need really more tools to understand what happens if your training dynamics require multiple mechanisms, and what happens if there is no unique solution to your problem. And I'm definitely not trying to say that whatever examples that I'm going to give are the only examples where mechanisms can interact with each other. There are many, many other examples. One of my favorite examples was this phenomena of grokking. So grokking is a phenomena in training neural networks or training many other models. What happens in grokking is you have if you are training some model, what would happen first is your training accuracy quickly goes from 0 to 100%. And your training loss also decreases very quickly, as you can see here. But your test accuracy and test loss are still very bad. And you might think that you are just stuck there and things are really not working. But eventually, after a long time, things will start working, and suddenly your test accuracy is very good, and your test loss is also good. And if you look more careful, there might be some other parameters that's also changing in between these two phases. There are many theoretical understandings of grokking in many different setups. In fact, if you were here for last year's meeting, we had some talk about grokking. But one particular explanation for grokking that came from this paper by Liu et al. And is understanding this from a change of training dynamics mechanism point of view. What they argue is that under their particular setup, the first phase of the training will have a kernel-like behavior. And because it has a kernel-like behavior, it will quickly allow the training accuracy to be 100% and the training loss to be very low. But you are fitting a kernel solution which, depending on your setup, you can make sure that kernel solution is not actually very good. And eventually, because in their system they actually have weight decay, after a long time, the weight decay kicks in, and as you can see, this dashed line, the norm of the parameter decreases. And when the norm decreases sufficiently, the system has to enter a feature learning regime. And once you enter the feature learning regime, that's when the test accuracy is actually improving. So this is an example of where you can have these different mechanisms that are happening in the same training trajectory. And in this case, it's first you will have a kernel behavior, and then you will have a feature learning regime. As promised, in this talk, I'm going to give you more examples, but most importantly, I will ask a lot of open questions. So I will talk about two examples. So part one is a work about benign overfitting for sparse linear model. This is joint work with Mo Zhou. The reason why this is interesting to me and why it's relevant to this talk is that the training dynamics for this particular model, even though it's a very simple linear model, is actually comes in the reverse direction. So we show that you are actually first in a more feature learning regime, and then you go into a kernel-like regime. And in part two, I will show you that if you try to look at an interesting problem of in-context and in-weight learning in transformers, you can train transformers and you can discover multiple possible circuits that can implement these tasks. And these different circuits are doing things that are completely different. So it's actually very hard to analyze the training dynamics here, and we have very limited theoretical understanding. OK, so first I'm going to go with the first part. OK, so I will first briefly talk about benign overfitting and implicit regularization. In the audience, there are a lot of experts in these areas. But if you haven't seen them before, the main idea is the modern models are all over-parameterized in the sense that the number of parameters is often much larger than the amount of training data that you have. And because of that, you have more parameters than your number of training data, which usually means there are many different minimizers that will have zero training loss. In fact, usually there are infinitely many of them that form some low-dimensional manifold. And we will call these minimizers that achieve zero training loss interpolators. And in deep learning, or in general, when you are training many over-parameterized models, very often you can make sure in your training you find one of these interpolators. Of course, among all of these infinitely many interpolators, many of them will not generalize well to test data, but some of them might. And what was surprising to people was SGD or any other training algorithm that you use typically converges to those interpolators that generalize really well. And this phenomena is often named benign overfitting because you are overfitting the data by getting zero training loss. But because you are getting there by a particular training algorithm, your generalization is still guaranteed. And the reason why this happens is still not completely understood, but people do understand why this happens in many simple models. And in these simple models, the explanation is often through what's called implicit regularization. So you can think of SGD or whatever other favorite optimizers you have. It might be trying to do something that's more than optimizing the loss function. So you can think that it might be choosing the minimizers with a certain property, in addition to making sure that for each data point xi and yi, you have f of xi is equal to yi. So this makes sure that your system is an interpolator. It, in addition, minimizes this regularizer, R of w. And this R of w, there are many examples. It can be many different things. It can be norms, many different possible norms, many possible definitions of margin, different relaxations of rank, and so on. So the idea is because your optimizer is converging to a solution that minimizes some of these quantities, it is able to find a solution that generalizes well. So that's called implicit regularization. So in the first part of the talk, we are just going to look at implicit regularization for linear models, where it's easier to prove a lot of things. OK, so we'll consider running gradient descent on mean-squared arrow with data points xi and yi. And you can think that the model is f theta of x is just an inner product between x and beta of theta. So both x and beta are in d dimensions, and d is much larger than n. So again, in this sense, we are in the over-parameterized regime. We have more dimensions than the number of data points, so we have infinitely many solutions. And we minimize this kind of mean-squared arrow. The implicit regularization for these linear models is very well understood. In fact, one of the first results on implicit regularization shows that if you do gradient descent on this very simple parameterization, you just use beta, right? If you run gradient descent from a zero initialization, it will find the minimum L2 norm interpolator. It will find the beta such that beta inner product xi is always equal to yi, and it will find the beta that has the minimum L2 norm among all the possible betas that satisfy all these equations. And what's also surprising is you can parameterize this system differently in order to get different implicit regularization. For example, you can parameterize beta with u Hadamard squared minus v Hadamard squared. By that, I just mean you parameterize beta I as ui squared minus vi squared, so coordinate y squared. You can also do this as beta I is equal to ui times vi. The two are kind of equivalent to each other. If you do this kind of parameterization and you initialize u and v with a very small initialization, it is understood that this will lead you to the minimum L1 norm solution. So you still have the system solving the equation that beta inner product xi is equal to yi for all I. But instead of minimizing the L2 norm of beta, you are minimizing the L1 norm of beta. OK, so as we can see, different parameterization actually leads to very different implicit regularization effects. Now with this, we are going to introduce the problem that we are solving, which is a sparse linear regression problem. The data is very simple. Your yi is going to be generated as beta star inner product with xi plus a noise. Here, xi is, for simplicity, we are just assuming xi are Gaussians, and the noise are also Gaussians. And beta star, the important structure for beta star is that it is sparse. Beta star is S sparse. And it's also important that beta star is of d dimensions, and d is still much larger than n. In this case, if you don't have noise, if this noise are always equal to 0, then we do know that minimum L1 norm solution is going to be a good solution under a large range of parameters. But it turns out if you have noise in your data, minimum norm interpolators perform really badly. So first of all, we do know that minimum L2 norm solution is never going to be good because even without noise, minimum L2 norm is not going to give you a sparse beta, and it's going to be very far from ground truth. And surprisingly, even the minimum L1 norm solution is very bad when you have noise. If you don't have noise, then sure, minimum L1 norm solution is very good. If you have noise and you insist on fitting the data perfectly, the minimum L1 norm solution is still bad because in some sense, a sparse solution is not very good at fitting the noise. And of course, we do know that this problem has a minimax rate that's roughly on the order of sigma times square root s log d over n. So if s is much smaller than n, you should hope you get a loss that's much smaller than what's written here. Question?
With respect to predicting new noisy labels or predicting F star?
Yes, a very good question. By test accuracy, I mean if you generate a new xi, I want to predict beta star inner product xi. If you predict yi, of course, there's always a sigma squared that you need to pay.
Thank you.
OK, so how do you solve this problem? Of course, one way to solve this problem is you still do minimum L1 norm solution, but don't force f of xi to be equal to yi. You just make sure that f of xi is close enough to yi. You don't get an interpolating solution. And then you will be in good shape. Question over there? Yeah.
From a bit counterintuitive, like it seems to be violating benign overfitting bias error in some sense. Why it pays like the 2 norm of beta star? Because we know minimum L2 norm solution can generalize if you have a slow decay in spectrum.
OK. The question is really why is there a lower bound here? The lower bound is here really because what we assumed about beta star, because we are assuming beta star is as sparse.
Oh, I see. You have astropic. Its spectrum is astropic.
Yeah, so the L2 norm solution is going to be a very non-sparse thing, and it's basically going to have the same error as 0.
So the features are isotropic.
Yeah, the features are isotropic, and there's no decaying in spectrum. OK, so yeah, as I mentioned, one way is to just do minimum L1 norm, but don't look for an interpolator. But can you do them simultaneously? A work by Muthukumar et al. Proposed a 2-step procedure that can give benign overfitting in sparse linear regression problem. So they can find an interpolator that's good in this way. In the first step, you find beta 1 that mostly recovers beta star. You can do this by L1 regularization. That's fairly standard. And in the second step, the problem with using beta 1 itself is that it's not going to be an interpolator. It's not going to predict the noise. In your second step, you are going to memorize the residual by some minimum L2 norm interpolator, beta 2. And then your final output is going to be beta 1 plus beta 2. So with this 2-step procedure, you have a solution that's interpolating the data, but still have good generalization performance. And they show that if you do it this way, you get a minimax optimal test error. The question that we are asking in this first part is, can we find such an interpolator by relying only on implicit regularization with some new parameterization and not do this 2-step procedure? Question?
is a very good estimate of 0. So
Yeah, beta 2
it's all about beta 1, yeah?
Sorry. So beta 2 is used to predict yi minus beta 1 inner product xi.
And
that's supposed to be very close to this noise Ci.
so the whole thing in the beta 2 here ends up being a very good estimate of 0.
Well, it ends up with a very good estimate of this noise here instead of 0.
No, on the sample it fits the noise, but in L2 it's a very good estimate of 0. So the whole thing is very much like the prediction that beta 1 gives, yeah? Which has the minimax rate.
Oh, right. Yeah. So I guess, OK, let me try to rephrase your question. The question is really, why do we really even
why
need
add in
beta
2? Yeah.
I agree that's not very clear. The only thing is to say that you can optimize all the way, and you don't need to worry about early stopping or anything. You can find an interpolator that still generalizes. Yeah.
To get good learning, because then you just wouldn't interpolate, right? Like if you just want to get good generalization, the right thing to do is not to interpolate. Is that correct?
Yes. Well, that one of the right solution is just not to interpolate.
So you're trying to say that it's possible to interpolate but still learn. So why not just memorize? I guess I'm trying to understand again. What are we supposed to get from this? This is, I presumably, it's not that you're suggesting this as a useful procedure. So what is the motivation, or what are you supposed to
get from this? The motivation of this line of work is just to trying to show that even in this case, interpolating doesn't hurt you too much. I agree that it would be better if there is a setting where training all the way and getting an interpolator actually helps you.
That's a perfectly good predictor. Really, it's just as well as the one. It's great. So it's a different.
That's not a linear predictor.
Why is it important for us to have a linear predictor?
Yeah, that's improper. This is a linear predictor, right?
Well, it's also improper. It's not sparse.
I mean, that is still
right.
It's linear.
Okay. I was wondering if I can first continue, because the reason I'm talking about this work is not particularly about how strong this motivation is, but I'm going to try to say I find this work interesting because the dynamic is interesting. Yeah, I mean, I agree that, I mean, there are good arguments to say that maybe you should just stop here, right? You don't need to go there. That I also agree to some extent. So, but if you really want to focus on getting to a 0 training loss, and we are trying to say that there is a way to achieve that. Okay, so our result says in the sparse linear regression setting, if you use this parameterization, then under some assumptions, you get an arrow that's roughly optimal. It's optimal up to some log D factors. What's interesting here is the parameterization is actually a combination of the minimum L2 parameterization, which is just this V, and the minimum L1 norm parameterization, which is this W and U part. And we balance the two by this additional parameter lambda, which is not trained, but it's something that we will select. So slightly detailed setup. The data, as I mentioned, y is going to be x times beta star plus noise. And remember, x is in this shape, so it has more columns than rows. X is a random matrix. Beta star is sparse. For this talk, we further assume that the size of the maximum and minimum entry are on the order of 1, although in the paper we can relax that. The learner model is going to be this one, as I promised. And the prediction is simply you inner product this beta with x. And training is also very standard. You run gradient descent on mean squared loss, which can be written this way. And for initialization, we basically just use the initialization that's standard for these two components. So V is initialized at 0. W and U are initialized to be alpha times the all ones vector with a very small alpha. Okay, so the main result restated is something like this. And I mentioned it works for x that are random, but it's also true for x with RIP property. And the arrow bound here is very similar to the lower bound for interpolator that was established in an earlier work. Yeah, as I mentioned, the reason I'm talking about this work and the reason I find this work interesting is because in order to prove this result, we actually need to analyze a fairly interesting training dynamics. So here's going to be the training dynamics. As you can see, if you train this model, what happens is that the training loss will first decrease to some value. And at the same time, the test loss is really significantly improving, meaning that in the first part, we are actually learning this sparse signal very well. But the training loss didn't decrease to 0. It decreases to a small value, but it's not 0. If you continue to train, the training loss will continue to decrease to a very small value. So that's when you get an interpolator. That does cost you to have a slightly worse test loss. Okay, I mean, this is in the log plot, so it's not that slight, but it's still not too much worse compared to the best test loss that you have. Okay, so this is, so there are clearly two phases of the training process. You can also view these two phases in the norm of the parameters. As you can see, this blue curve is the norm of the L1 component. It increases to a very large value in the first phase and basically stays there. The orange curve is the norm of the L2 component. It increases fairly consistently throughout the two phases, but its effect is eventually felt at this point. Okay. So in stage 1, basically the L1 component, so I will always call this the L1 component. The L1 component will grow large to recover the signal, and the L2 component V will remain small. And in stage 2, the L1 component will not move much, and the L2 component will grow to memorize the noise and remain small so that it doesn't hurt your test accuracy by too much. Of course, one benefit of this is you can train to the end without worrying about when to stop. But I mean, I do agree it's a minor benefit. But what was interesting to me was this is a dynamics where feature learning actually happens first, and L2 or kernel kind of behavior happens later. And in order to analyze this dynamics, we had to come up with some interesting ideas. So the main challenge in the dynamics analysis is that ideally, I want to do this two-phase training process. Maybe in the first phase, I fix V and only train the L1 component. And after I do that, I want to fix my L1 component and only train my L2 component. If I do a training process that way, then it will be very easy to analyze. However, we are not doing that, right? In the real dynamics, both the L2 component V and the L1 component are moving. And when they are moving simultaneously, we need some new ideas to characterize the dynamics. And the first idea that we had, and the natural idea that everyone probably would try is, okay, in the first stage, V is small, right? We know V has to be small. And part of that is because gradient on U and W are larger. So maybe we can just view V as a perturbation and just brute force through the L1 norm proof and try to see if that works. Unfortunately, that actually doesn't work because the L1 norm proof is fairly delicate, and having this V as a perturbation just breaks the proof completely. So the idea that we have to fix that is we actually have some ideal dynamics for V. So our hope for V is it will memorize the noise when there is no the L1 component and when there's also no signal. So we know the ideal V will follow this dynamics. And this dynamics, of course, we understand very well. This is just a least squares dynamics. This will allow us to explain why V is very small. So our idea is actually we will approximate V with this ideal dynamics. This gives some formulas which can be further simplified when X is Gaussian. So using this approximation, we show that V is always very close to this approximation. And this V is close enough to this approximation so that even if we consider the difference as a perturbation, we can still analyze the whole thing. Yeah. Yes. So by following the dynamics, I mean, it follows. You can analyze the gradient descent for this V, and let's call that V star. And we want to argue that V is close to V star at any time. OK, just to conclude part one, it shows that there's actually no inherent order between the kernel regime and the feature learning regime. It's possible that feature learning regime happens first. It's also possible that kernel regime happens first. It suggests that when the two mechanisms are competing, the dynamics with larger gradient will win. And here I have an asterisk because I don't mean larger gradient in a L2 sense, but more in a function sense, that the one that has the largest influence on the function. And we also see that changing the architecture or parameterization can change which mechanism comes first. And in this particular case, we have to change this value of lambda carefully in order to make sure that the feature learning regime happens first. OK, any questions before I move on to the next part? OK, if not, I will talk about this more recent work about in-context and in-weight learning in transformers. In-context and in-weight learning are new concepts in large language models. In-context learning means you are giving these examples. Suppose, say, you want to solve a sentiment classification task. Then you give your model a few examples. And the model will try to learn from the examples you give to try to classify this new query. So that's called in-context learning because these part of examples are what's considered to be context. And in-weight learning just doesn't provide these contexts and just asks the model to directly make a prediction. OK, so, but of course, analyzing in-context and in-weight learning in the regime of a large language model is going to be particularly challenging. So we are going to focus on very basic, much simpler tasks. And this setup actually came from the papers of Chen et al. And Reddy. So in their setup, there are going to be k in-weight learning classes. Think of these as Gaussians that have different centers. What's important is just if two things come from the same class, they have a very large inner product. If two things come from different class, they have smaller inner product. That's the only important property that we're going to use. And there are going to be L labels. The input is going to be a sequence of n pairs of item and labels, followed by a query item. The goal is to predict the label of the query item. And how do you predict that? I will give you some examples of types of sequences. The types of sequences considered in these works is that you can have different types of sequences corresponding to different tasks. An in-weight learning sequence is a sequence like this. As you can see, different colors correspond to the class of the item. As you can see, the class of the query doesn't appear in the context, right? So if you didn't know what the label for this class is, looking at the context is not going to help you. So only way you can know what is the correct label here is if you have memorized these in-weight learning classes and you know that this blue class should have a label 2. So the question mark here, you should predict 2 as the label. So that's why it is called an in-weight learning sequence. The context is still provided just for uniformity of the input, but the context actually doesn't help you at all. You have to rely on what you have seen before. And then there are in-context learning sequences. These ICL sequences, the items are not from the known classes. As you can see, these colors are different from these colors. So they are from totally unknown classes. So even if you have memorized everything you've seen in the training data set, that's not going to help you. What is going to help you is that the query item will share the same class as one of the items in context. And as I mentioned, you can, in this simplified setup, you can easily see that by just doing inner product between xq and x2 and seeing that inner product is the largest. And now, because you can see that, you know the correct label for xq is going to be 3. So in this case, whatever you memorized in weight, these classes are not going to help you. But you have to look at the context in order to make the correct prediction. In these works, they also have what's called a bursty ICL sequence, which is very similar to ICL sequence, but instead of the query item only shares the same class with one item, the query class here is going to share the same class with exactly B items. And you can, as long as you find either of them, you know the correct label for this instance should be 9. Okay? So we are going to try to solve these tasks using a transformer. So here's a quick overview of transformer, although I'm sure most of you have seen it already. So you have these input sequence, which you will turn into an embedding, where every column corresponds to one token in the sequence. For this one, you will map it to a set of keys by some weight matrix WK. For each token, you will also map it to a query by another weight matrix WQ. And you will do the inner product between these query with the keys. And that gives you some raw attention scores. And with the raw attention score, you do a bunch of things. You can do a causal mask, which means everything can only attend to the things that appear before. You then do a softmax, and then in this format, you do a transpose. And after that, you read out the result by some output value matrix. And written mathematically, you can write it in this way. What's important to know is really everything can try to attend to all the previous tokens based on how similar it is to the previous tokens, where the similar is defined very vaguely. It's something that you can customize. One problem in analyzing these transformers is that this set of parameterization is actually highly redundant. First, clearly, part of the redundancy is here you have the product of WK transpose and WQ. And we only care about the product. We don't care about the individual matrices. So we will just call this matrix A, and we will not have two separate matrices for them. Another redundancy often comes from this PV matrix. OK, so there is a residual connection. So technically, you can't just get rid of this immediately. But imagine if there's no residual connection, if there's no EI here, my output is just this WPV times E times SI. Then it's kind of redundant because in the next layer, because then it's just a linear transformation, right? In the next layer, I can apply this linear transformation in the next layer, and it doesn't do anything. It doesn't change anything. So that's another source of redundancy, and that's part of the reason why if you train a transformer in practice, it's often hard to interpret its weight matrices because they are often randomly rotated due to this PV matrix. One way to get around that issue is to use a new architecture called disentangle transformer that's in this paper by Channy et al. So their idea is simple. So instead of using a residual connection, you will have E to be the output plus the original input. You will simply concatenate your output with the input. So maybe your original input is 3-dimensional. After one attention layer, you have a 3-dimensional output. you will just concatenate the two to get a 6-dimensional vector. And then in the next layer, you double it again and get a 12-dimensional vector. And then, and because you are doing this concatenation, now you no longer need to have any value matrix. Anything a value matrix can do, a further linear layer can also do. So you don't have to have the value matrix, and you don't have these arbitrary random rotations in your solution. Of course, I'm not suggesting that this is a practical way you should train your transformer, because of course this quickly becomes intractable as your number of layers increase. But it is a good model for theoretical analysis, because within 1 or 2 layers, this doesn't blow up things by too much, and it allows things to be easily interpreted. In practice, we train a 2-layer disentangled transformer, and it actually performs fairly well for both ICL and IWL sequences. But for this talk, I'm going to particularly focus on the in-context learning examples. As you can see, for different parameters, the ICL accuracy almost always go to 100%. And you can probably already see that there are some interesting phenomena that's happening where the ICA accuracy first reaches some plateau, and the value of the plateau is surprisingly similar to B over N. So B over N, remember B is the number of times that the same class of the query appears in the context, and N is the total length of the context. So B over N is the fraction of things that agrees with the query. And the larger that is, it seems like the better the first phase accuracy is. So the question is, how does this disentangled transformer learn in context learning? And at first, we thought there should be a very simple mechanism that we can understand. And once we understand that, we can prove that that's how it's done, right? But it turns out when you actually train these and you look at both the weight matrices and the attention patterns, they are fairly messy. They are not as clean as we had hoped. And after some experiments, we realized that there are many different ways for this, even for this very simple 2-layer disentangled transformer, to learn in context learning. And in order to understand that, what we did was we look at these attention matrices. So first of all, I didn't mention, but our embedding always have a positional encoding. So for each token, it first has a positional encoding, which is just hard-coded. Position I is encoded as EI, the I spaces vector. And then you have a data. So the first attention matrix, in some sense, has 4 blocks between position and position, between position and data, and so on. And the next attention matrix, because we are using this disentangled transformer, becomes an even larger matrix because we are concatenating the output. So it has components for input position, input data, layer 1 output position, layer 1 output data. So it becomes a much larger matrix. And if you just train it, you observe that many of these matrices are 0, like no matter how you train it. But many matrices are not 0. Which are the matrices that are not 0 in these blocks. What we did was we tried to select a subset of matrices and train them and see if they can still perform the ICL and IWL tasks. And by doing that, we found that there are many combinations that actually, when you just train those matrices and set all the other matrices to be 0, you achieve 100% ICL and IWL accuracy. I will highlight 2 of them. So one combination that works is if you train these 2 orange matrices. And another totally different solution that works is if you train these 2 matrices. So let me explain what they do. Okay. So the first ICL circuit is actually the circuit that we had in mind. So this is something that's fairly well studied called induction head. So the way induction head works, So I'm, in all of these illustrations, I've hided a lot of unnecessary details. And I've only shown you the important part. For example, there is a positional encoding for these, but I didn't show that. What an induction head does is, in the first layer, it makes sure that every label position will attend to its previous position. So position 2 attends to position 1, position 4 attends to position 3, position 6 attends to position 5. And you can do that just by utilizing the positional encoding. Using the positional encoding, you can make sure to do any fixed pattern of attention. Well, in a more general induction head, usually each token attends to the previous token, but in our case, because these pairs are independent, it doesn't really make sense for this one to attend to this one. It doesn't do anything. Okay, so with this induction head, what happens is after the first layer, the output for this is going to be x1. The output for this position is going to be x2, and the output for this position is going to be x3. And remember, the input is still preserved because we are concatenating things. And these positions are not going to be relevant, so that's why I didn't draw them. And now in the second layer, what we can do is, as you can see, we have the xq here, right? We can compare this xq with each of the output of the first layer and see which one of them is the most similar, which one of them has the largest inner product. That we can do easily by using attention, right? And the network will easily see that xq is most similar to x2. And therefore, the output should be 3. So that's how the attention head works. And indeed, if you train only these networks, you get the intended weight matrices, an identity here and a staircase structure here. What was surprising to us was there is actually a different way to solve the problem that we now call reverse induction head. What reverse induction head does is, in the input, you actually don't look at the positional encoding, you look at the data. You compare the query data with all of the data that you have here, and you look at which one is it most similar to. Well, I mean, clearly it is most similar to x2 and itself, right? So it is most similar to these two. And you only care about the output on the positional encoding. So we still have the data and positional encoding from the first layer, and we look at the output of the layer 1 position at the positional encoding part. And because it is similar to these two, the output should be E3 plus E7. In fact, should be E3 plus E7 over 2. I just couldn't fit it on the slide. But it's a combination of these positions. And of course, if it's a bursty sequence, if there are multiple things that are in the same class, it's going to be a combination of all of them. Now, from this one, I can look at this positional encoding, and I will say, whatever position I have here, I always attend to the position that's one after it, which is something that I can do by a fixed design matrix, by looking only at the positional encoding. So in this case, I will only attend to this E4, because E7 doesn't have anything later than that to attend to. And once again, I attend to the right thing, and I can output this label 3. So this is exactly the reverse version of induction head, because in induction head, the first layer uses positional encoding, and the second layer compares the data. This one first compares the data and then do the positional encoding. So, but it gives the same result. And in fact, we can find other circuits that are doing slightly different things. And if you train these matrices, again, you get results that are as expected. Okay, in these matrices, you see some additional parts, and those are useful for in-weight learning, which are not totally relevant for this talk here. And the existence of these multiple circuits makes theoretical analysis very challenging, and right now we only have very preliminary analysis. In order to analyze the system, we have to make major simplifications. We have to assume only weights related to induction heads are trained. Then that focuses the result on a single circuit. And instead of end-to-end training, we will have to do a 3-stage training where we first train the output layer, and then we train the layer 1 attention, and then layer 2 attention. The behavior is similar, but still not the same as actually training everything together. With these major simplifications, we can show under reasonable parameter choices, the network learns both in context learning and in weight learning. And as a corollary, we do know that if you just first train the output layer, the output on an ICL sequence is just going to be a random label that appeared in your context. And because the probability that that is correct is B over N, your ICL accuracy is B over N in that phase. So at least we understood that part. We can also have settings where if you have some large noise, remember I said these classes are Gaussians, so if the Gaussians have larger variance, and if you make some different choices on some parameters, there are cases where ICL will fail, but in-weight learning still succeeds. So in general, in practice, there seems to be some competition between in-context learning and in-weight learning. You can create situations where one of them succeeds and the other doesn't. OK, so just in conclusion for part 2, we see that even in this very simple transformer, which is just a 2-layer transformer, right, and disentangled, there are often multiple ways where you can also call them multiple circuits to complete the same task. And this is not only for the task that I've described. This actually has been observed in some earlier work on these tasks of completing the brackets. Simple transformer model can be made more interpretable by using a disentangled version and freezing certain weight matrices, but then the training leads to different results. Training dynamics analysis is doable for a single circuit, but it is still a huge open problem to what to do if you have multiple circuits that can all happen at the same time, which is why I said the talk is more about open problems. So let me end by open problems. So I was wondering what are some techniques that we can use to analyze the training dynamics when multiple circuits are possible. Some time ago, before people are analyzing these training dynamics and trajectories, there were even simpler problems where we could characterize the optimization landscape, and we know all the possible local optimal solutions and global optimal solutions. And in those cases, we didn't care too much about how many optimal solutions are there or what is the trajectory. But for these more complicated problems, those are no longer possible, and we switched to analyzing the training dynamics. But when you analyze the dynamics, it seems like it's most natural to have a unique trajectory to a unique solution. So is there a way to combine the two? That's some questions that I'm hoping we, as a community, can answer. And another thing is, how can we, given that there are these competitions both between different mechanisms and also between different circuits or even between different tasks, how can we encourage or discourage competition between different mechanisms? Can we, for example, use more parameters, and that will make it less problematic if things are competing with resources? Or can we do something to encourage competition? And maybe there are some good use cases for that. And I'm also interested in whether there are other setups where analyzing competition could be important. One thing that I have in mind is maybe in problems that are related to multimodality. Say if you want to predict something based on both images and text, then you can get information from images, you can get information from text, and there is certainly some competition between where do you get your information from. If you don't train them carefully, you might only get information from one source. So in those cases, can we carefully change the parameterization so that the competition happens in a way that's beneficial to us, and to make sure that we use information from both sides? That seems to be an interesting open problem, but it would require a formalization that allows theoretical analysis. And I'm sure there are many other setups where this kind of competition phenomena would be interesting. With that, thank you, and any questions?